Okay, this is part 2 of the curve sketching polynomial. This is the PDF that goes through all the steps on curve sketching. We've completed this step right here, which is to find f prime, local maxes, local mins, intervals of increasing, decreasing. Now we're going to move on to this step where we are to find f double prime and find all places where f double prime equals 0. Find when f double prime does not exist. Do the number line, much like we did with the critical values, find points of inflection, change in concavity, things like that. And then we will sketch, which will be the final part of this video. So now we need to find f double prime. Okay, let's find f double prime first. F double prime. Okay, go back a couple seconds to recall what the first derivative is, but when you take the second derivative, you're going to get 60x cubed minus 30x equals, we're not there yet, just this is the second derivative. Now what we're going to do is figure out when the second derivative equals 0 and when the second derivative does not exist, because now we're talking about concavity. And that has to deal with the second derivative. So it's like finding critical values, but to the second derivative. Okay, so we have 60x cubed minus 30x equals 0. And over here, when does the second derivative not exist? Well, again, it's a polynomial. And polynomials always exist, so we're not going to have a problem here. Here, I can factor out, it looks like a 30x. Leaving me 2x squared minus 1. Alright, so I'm going to set each of these equal to 0, because that's how we do this. So once it's factored, set each factor equal to 0 and solve. So x equals 0, 2x squared equals 1, x squared equals a half. So x is going to equal plus or minus square root of a half, which is roughly plus or minus, let's say just 0.7. So these are all potential inflection points, because remember, critical values to second derivative were those inflection points, which we'll do in a second. Okay, so let's draw a number line, and we're going to do the whole plot a number from each region in. So our critical values from the second derivative were 0.7, negative 0.7, 0, and a positive 0.7. Okay, so we need to pick numbers from each of those regions. I'll just pick negative 3, negative 0.1, 0.25. Again, as long as they're in the region, you're okay. It doesn't really matter what those numbers are. And then 1. Now, again, recall that the second derivative is 60x cubed minus 30x. This is what we're plugging our stuff into. So the number in this region I'm going to pick is negative 3, and I'm going to plug that in to the second derivative. And you evaluate that, and I did not, there it is, negative, sorry, I couldn't read my calculator, negative 1,530. Now since that is negative, it means we are concave down. Okay, so I'm going to come over here in this region and I'm going to say concave down. Now the second derivative at negative 0.1, I think you get the idea now on how to plug it in. We are going to get 2.94, which is positive, which means we are concave up. So concave up in this region. Then f double prime at 0.25. That's going to give me negative 6.5625. Again, that is negative, so that we are concave down. And finally, the second derivative at 1, which is just going to give me 30, which is positive, and that is concave up. So concave down, concave up. So the interval is a concavity. We are concave up, looks like from negative 0.7 to 0, and then again from 0.7 to infinity. we're concave down from negative infinity to negative 0.7. Again, I'm just reading it right off the number line. And where are we else? 0 to 0.7. So how about inflection points? Inflection points would be points on the graph, so they have to exist. So like asymptotes and stuff like that, that don't count. But we change concavity. We change concavity at negative 0.7, 0, and 0.7. Notice, because we're down, now we're concave up. Concave up, now we're down. Down, now we're up. So those are all points. But remember that inflection points, they are points, so we need to figure out the y value. Now the y value, you would have to plug it back into the original function. Recall, the original function is 3x to the 5th minus 5x cubed. And that's going to give me 1.21. And then our other one was negative 0.7. And plug that into this function, you're going to get negative 1.21. And our third one was 0. When we plug that into our function, I think it's easy to see you're going to get 0. So we have all the information we need to sketch. Here's a summary of everything we've just done. So let's go ahead and start the graph. We have intercepts at negative 1.29, the origin, and positive 1.29. We have a local max at negative 1, 2. And I'm going to do something like this to remind myself that it is a max. At positive 1, negative 2 is our min. So I'm going to do something like that. What else do we have? Inflection points. So negative 0.7, 1.21. That puts me probably around right there. I'm going to label that as an IP. This is also an IP. And 0.7, negative 1.21. So that puts me somewhere like right here. Okay, now the increasing, decreasing part. All right, we've already kind of done this in another video where, you're just connecting the dots, which is what I'm doing here. And that's really what my graph's going to look like. It's just now, how is it going to look? How is it going to curve? And I'm going to connect the dots, but now with the concavity, because concavity is how I'm going to be connecting dots. So from negative infinity to negative 0.7, here's that negative 0.7. So from negative infinity all the way out to negative 0.7, we are concave down. All right, so that looks like that opening down parabola. And then from negative 0.7 to 0, says right here, we're concave up. So we'd connect it like that. We'd flatten out here because this is also a critical value, if you recall. So we do have a slope of 0 here. Now from 0 to positive 0.7, we are concave down. Right there. So connect these 2 points, but concave down. So a parabola looking like it's opening down. Then finally from 0.7 to infinity, we're concave up. Make sure you're passing through all the points. And this is my graph of, 3x to the 5th minus 5x cubed.